always involve a number of degree of indeterminacy. Okay, so if continuous beam structure usually is indeterminate structures, and it's very difficult to get the solution. For example, the internal forces by hand. Okay, and so in design code, okay, usually for for continuous beam, okay, some table, okay, provided to obtain some maximum bending moment for interior support, for end support, for some locations. Okay, but the plastic analysis for continuous beam, I will show you, is very easy to do. Okay, so sometimes the plastic analysis is much easier than elastic analysis. So this is a 3-span continuous beam. Okay, we have 3 external forces, and then we do plastic analysis. Okay, so for multi-span beam, okay, each span may have a different section, so different plastic moment will be for different spans. Okay, so first span maybe have a different plastic moment from the second span. Okay, and at the support location, because support, okay, at support, okay, is connected to spans. Okay, so at the support location, we have 2 plastic moments. One is from the left span, the other one is from the right span. So we have 2 plastic moments, but in reality, we can only have collapse in one value. Okay, so we have to select, okay, one value as the plastic moment, because only one plastic hinge at each support location. Okay, so here I introduce the rule of 3. At support, the plastic hinge forms at the plastic moment of the vehicle member. So when 2 members are connected at the internal support location, definitely the plastic hinge will occur at the vehicle side. Okay, it's very easy physically. So you just need to understand when 2 values are available at the support location, you just need to select the smaller one. Okay, the lesser value. Okay, you just need to select the lesser value. That's all. Okay, and also it is almost impossible that every span will fail simultaneously. So each span must be checked individually. So this is the reason why, okay, the plastic analysis for for continuous beam, okay, is easier. Okay, because you just need to consider the collapse of individual span, okay, one by one. That's all. Okay, because when the plastic hinge forms at the support location, this plastic hinge already destroys, okay, the continuity for the 2 spans. So it's very easy to understand why we just need to analyze, okay, span by span when we do the plastic analysis for continuous beam, because we always have plastic hinge at the support location, because at the support location we have a maximum hogging moment. Okay, so plastic hinge forms at the support location, and when the formation of the plastic hinge destroys the continuity, because the rotation is allowed at the plastic hinge location, because this is a hinge. So when the rotation is allowed, that means the continuity, okay, is destroyed. So you just need to analyze span by span. Okay, and the collapse is a partial collapse. Okay, maybe a collapse occurs at the first span, and other spans, okay, keep on collapsed. So this is usually for continuous beam, this is a partial span, because just, okay, several span collapse and other span, okay, keep, okay, uncollapsed. Okay, so this is a case for continuous beam. So when we have this understanding, it's very easy to do the collapse analysis. For example, for this structure, okay, we have 3 spans, because structure is symmetric, and the applied forces also symmetric. So you just need to consider one side span and one internal span, because the second side span same as the first side span. So the two side span will collapse, okay, simultaneously. Okay, so and then you just need to analyze the collapse for the first span and the collapse for the second span. So in the first case, when the collapse in the first span, this is the end span. So point A is simply supported. So it is impossible, okay, to have a plus hinge at the point A because it is simply supported. So for simply support, okay, there is no moment resistance capacity. So here the moment is always equal to 0. And when the first span collapse, okay, it's a plus hinge at the point B and the plus hinge at this point internal, okay, look, internal plus hinge at the force application location produced, okay, according to the rule 1 and rule 2. According to rule 1, okay, plus hinge at the point B, okay, as the section at the point B is a plus hinge because this is a restraint end. And according to rule 2, at the force application location, this is a plus hinge location. So in the first case, for the collapse of the first span, we have two plus hinges. Okay, we have two plus hinges. And then, okay, this is a case same as the previous example. This is same as a prop-pit cantilever because one end is simple support, the other end is fixed end. So this is same as prop-pit beam structure. In the prop-pit beam structure, we already obtained the solution. So you just need to use the formula given here. So from this example, we have obtained the collapse weight for the prop-pit cantilever. So this is the same as the end span for continuous beam because one end has a 0 moment, the other end has moment equal to the plus moment. Okay, so here is the solution we already obtained. So you just need to use, okay, the solution given here. Of course, you can establish, okay, the equilibrium equation and then, okay, to obtain the solution. Okay, so this is a case for the first span. Okay, this is a case for the first span. So here, this is a solution from the previous example 5. Of course, you can use the equilibrium equation because the actual moment plus reactant moment is equal to free bending moment. So the real moment is equal to, how about the real moment? Okay, I still have to mention several issues. Because we have two values, okay, for the first span, at the internal plus hinge, the plus moment must be equal to 600. Okay, 600 because we only have one value. But at the plus hinge at the point B, we have two values. One is 600 from the left side, and the other one is equal to 900 from the right side. Okay, but according to rule 3, okay, the plus moment at the point B is equal to the vehicle value, so it's equal to 600. So here is equal to, okay, so please understand, the plus moment at this location is equal to, okay, 600. Again, here is equal to 600. Okay, so the actual moment is equal to 600, and the reacting moment is equal to linear interpolation between 0 at the left and 600 at the right. Okay, so it is equal to 600 over 2 if this is the middle. But now, here, if this is the middle, so it's equal to 0 plus 600 over 2. Okay, and how about the free bending moment? The free bending moment, you just need to consider beam is a simple support. So for simple support beam, subject to the concentrated force. The concentrated force is equal to this force. Okay, is equal to this force. Okay, so for the sine span, the plus moment for both plus hinge, okay, equal to 600. So here is a solution. Okay, so you can use a standard formula, or you can establish the equilibrium equation by yourself, and then from the equilibrium equation you can get the solution. Please understand, the moment at the 2 plus hinge is both equal to 600. Okay, 600. And then we go to the internal, the second span. This is the internal span. For the internal span, the moment at the 2 ends, okay, both not 0. Okay, so this is equal to plus moment. And for point B, we use a lesser value. Lesser value is 600. And for point C, again, we use a lesser value. So it is equal to 600 again. But for the internal plus hinge, okay, because internal plus hinge is at the middle of the span, so it is equal to 900. Okay, so please understand. Okay, for the internal span, for the second span, okay, how about the real bending moment? The actual bending moment is equal to 900. Okay, because this is the internal plus hinge, and for the second span, the plus moment is equal to 900. So this second term is the actual bending moment. This is the actual bending moment. Okay, and how about the reactant bending moment? So reactant bending moment is equal to linear interpolation for the bending moment at the 2 ends. Okay, at the left end is equal to 600, at the right end is equal to 600 again. So the linear interpolation must be equal to 600. So the 600, this one is a reactant moment. This is a reactant moment. Okay, and how about the free bending moment? The free bending moment, okay, for single concentrated force is equal to W times A times B over A. Okay, but now the W is for the internal span. The W is equal to 1.5 WC. So this is the 1.5 WC. It's different from this force. Okay, so we can obtain the internal, the collapse force for the second span. Okay, and I want to mention another case. Okay, for example, if the second side span, the sole span, okay, has a plus moment also equal to 900, and then at the point C, the plus moment is equal to 900. Okay, so when point C, the plus moment at the point C is equal to 900, and then the reacting moment is not equal to 600. Okay, so reacting moment is equal to linear interpolation between 600 and 900. Actually, it is equal to 600 plus 900 over 2 because it is at the middle span. Okay, so please understand how to change. Okay, how to change when I change the question. Okay, I just need to do a little bit change about the question. Okay, and then we have obtained two values. One is 333 and the other one is 450. So which one is a real collapse mechanism? Of course, the second one. Okay, because when you apply, okay, the external force equal to 333, the second span, the internal span already collapsed. Okay, so the structure is already partial collapsed. So that's this is a collapse force. But actually, when we apply this force, the two side span, do not collapse. Okay, do not collapse. Okay, because only when the force is increased to the 450, okay, the two side span will collapse. Okay, so this is a solution. Okay, the solution, and here is a result. Okay, so because this is a collapse mechanism. Okay, so we have 3 plus hinges, and there's 2 plus hinge at the interior supports, okay, destroy the continuity. So it is easy to obtain the bending moment. Please understand, okay, it is easy to obtain the bending moment. Why? Because, for example, we already know the collapse force. So you just need to collapse force here, and here is equal to 1.5 WC. Okay, so you apply force. And then at this location, because we know moment is equal to plus moment is equal to 600. So just need to apply, you can separate here. You can separate here and then apply a moment at the right end. Okay, because moment here is equal to plus moment. So this is a simple support beam, right? This is a simple support beam. So simple support beam, subject to external force and applied moment. So we're always able to obtain the moment diagram. And similarly for the internal span, you just need to apply the moment at the two ends and also apply force, and then you can obtain the moment diagram for this simply support beam. So each one actually is equivalent to simply support beam subject to the original external forces plus moment. Plus moment, because at the plus hinge, the moment is equal to plus moment. So just need to apply the plus moment. So we can obtain the moment diagram, the moment diagram for each span. And then we can do the moment check, because we assume, this is a correct mechanism, so the force and the source span, do not correct. That means, the force application location for the force and the source span, are not plus hinge. So the moment for this point and the moment for this point should be less than, the plus moment. Should be less than the plus moment. So this is less than the plus moment, and also here's less than the plus moment. I will talk in detail how to calculate the moment for this location. You can try to get the solution first, and maybe next week I will show you how to obtain the moment for this location and for any other cross sections. And this is a general case. For multi-span continuous beam, but now the beam is subject to distributive force. When the beam is subject to distributive force, the problem becomes more complicated. Why? Because force is distributed. So we don't know the location of the internal plus hinge. Of course, we still just need to analyze the continuous beam span by span. So it is like single span. But when force is a distributive force, we don't know the location of the internal plus hinge because we don't have a rule to determine the internal plus hinge under the application of distributive force. Of course, when structure is symmetric, when the force is uniformly distributed, we can guess, the internal plus hinge at the middle of the span. But for example, for the side span, one end has a zero moment, and the other end has a non-zero moment. So definitely it is not symmetric. So when the structure is not symmetric, you have to determine the location of the internal plus hinge. So this is a difficult part. So now I show you how to obtain the location of the internal plus hinge. So firstly we just need to consider two cases. One is interior span. The second one is end span. Because all interior span have the same correct mechanism. So this is case one. In case one, there are only two correct cases. For the internal span, we have the plus moment, the moment at the two ends. The moment at the two ends both not zero. Both not zero. So we have a moment here and a moment here. In this special case, the moment at the left end is same as the moment at the right end. But in general case, maybe the left span has a different cross section from the right span. So maybe MP is different. Maybe MP is different because MP is equal to the lateral value between the two adjacent spans. So when, for example, the middle span, this interior, this span, the plus moment for this span is equal to MP. But for the left span, maybe the plus moment is equal to MP over 2. When this is the MP over 2, the plus moment here should be equal to MP over 2. So the structure becomes unsymmetric. So even for the interior span, we still have a possibility the structure is unsymmetric. Do you understand? But of course, in this case, we definitely, because structure is symmetric, force is symmetric, so we know the plus moment must be at the middle of the span. But for the side span, we don't know, okay, because at one end has a non-zero moment. It is equal to plus moment, but for the other end, the moment is equal to 0 because this is simply supported. So we don't know the location of the internal plus hinge. So how to determine the location of the internal plus hinge? Because the internal plus hinge must occur at the section with a maximum bending moment. Because when this section achieves the maximum bending moment, this section becomes plus hinge. Okay, and the maximum bending moment is equal to the plus moment. Okay, so the cross section with the internal plus hinge must achieve the maximum bending moment. The maximum bending moment means the first derivative of the moment about x is equal to 0. So we use this formula to determine the location of the internal plus hinge. Okay, and also according to the bending beam theory, the first derivative of the m is just equal to shear force. So because this is equal to 0, that means the shear force is equal to 0. So it is so we can have a very useful conclusion. Okay, if you want to find the location or section of the internal plus hinge, you just need to find the section with a 0 shear force. That's all, with a zero shear force. Okay, so we can, okay, so for the first case, okay, so now we consider the first case. For the first case, we have two span. We have an interior span, so the plus moment at the two ends must be equal to the plus moment. Of course, x must be equal to L over 2, but I'll show you how to obtain x equal to L over 2. Okay, so we cut the section at the internal plus hinge location. Okay, we cut the span, we cut the beam in the internal plus hinge location, and then when we cut off the structure at the plus hinge location, the moment is just equal to the plus moment because this is a plus hinge. So the moment for this section is equal to MP, and this is the second moment. Okay, so the second moment produces a tension. So this is the direction of the second moment. So this second moment, and also we have a conclusion. The shear force at the plus hinge section is equal to 0. So here the shear force must be equal to 0. Okay, so please understand why I didn't show shear force here, because shear force here for this section is equal to 0. Okay, so this is the reason why I didn't put the shear force here. But at the two ends we have a shear force. At the two ends we should have the shear force. Okay, and then we can establish the equation. Okay, usually when we establish the equation, we can establish the equation for the left free body or for the right free body. Okay, usually when we establish the moment equilibrium equation, we take the moment about the cut section. Okay, about the cutting section. But now, please understand. Okay, if you take a moment for the cutting section, your solution is incorrect, because if you take a moment for cutting section, we still have one more unknown because we don't know VA value. Okay, we don't know VA value. Okay, so you have one more unknown. So when we do the plastic analysis, please take a moment for at the support location, because the shear force at the cut section, at the cutting section is equal to 0. Okay, in the elastic analysis, we don't know. Okay, the shear force at the cutting section is not equal to 0. So in order to eliminate the shear force in the moment equation, we take a moment for the cutting section. But in the plastic analysis, because the shear force at the cutting section is equal to 0, so please take the moment about point A and the point B. Okay, I want to emphasize this point because in the past examination, many students take a moment for the cutting section, and their solution is incorrect. Okay, their solution is incorrect. So please take a moment for support A for the left free body and for point B for the right free body. So we can establish two equations. Okay, we can establish two moment equations for the left free body and for the right free body, and then we can represent. Okay, we can represent each equation, okay, in term as expansion about NP, okay, NP or 2NP or any 4NP, something like this. And we always able to obtain two equations, okay? So from two equations, we can eliminate NP. Okay, we can eliminate NP. What's the meaning of eliminate? You just need to make this term equal to this term, okay, because both are equal to NP. So we can obtain one equation about x, just one equation about x. And the W can be eliminated from two sides, okay? So we can obtain the equation about x. And please understand, from this equation, usually we have two solutions about x. Okay, we always able to obtain two solutions about x because when you take a square root, we have a negative and a positive. Okay, negative and positive. So we have two solutions. But okay, please try to obtain two solutions first. Okay, and then the solution between 0 and arrow, because this is a cutting section, so definitely physically x must be between 0 and x. Okay, so the solution between 0 and arrow is always unique. It's always unique. So you just need to pick up the solution, okay, between 0 and arrow. Of course, in this case, x is equal to arrow over 2. Okay, because structure is symmetric, force is symmetric, so we can obtain. For example, in this case, okay, the W, okay, the W is a constant value, so we can eliminate. For example, when W is a function about x, maybe we have to use a different formula. Okay, when W is not uniform distributed, maybe okay, the W for the left side is different from the W for the right side, so you should have a different equation, and x is not equal to arrow over 2. Okay, when force is not uniform distributed, for example, maybe I will change, okay, the force from the uniform distributed to linear distributed. That's all. Okay, so please understand. Okay, here will be not just equal to W, it is equal to W times x, and the solution about x is not equal to arrow over 2. Okay, so please understand. At this point, after obtaining x value, you just need to go back to here and here to obtain NP value. When NP is given, you can obtain the lambda value. Okay, so when NP is given, we can obtain the lambda value. When lambda is given, we can obtain NP value. NP value means the required moment resistance. Okay, plus moment of resistance. When this required moment of resistance is determined, we can select the cross section. Okay, because we can obtain the plus modulus required. And based on the required plus modulus, you can determine the cross section to make the plus modulus, okay, larger than or equal to the required, okay, plus modulus. So this is a design based on the plus analysis. Okay, so if we do the classical analysis, you just need to obtain the load factor. You just need to do the collapse loading. But when you do the design, okay, usually we provide you a required collapse force or required load factor. For example, I hope you do the design to achieve the load factor equal to 1.5 or 1.6. Okay, so this value is given. And then from this equation, you can obtain the required NP value. Okay, when required NP value has been determined, and the NP value over yielding stress is equal to required plus modulus, right? So this is, we know the required plus modulus, and then you can try different cross section of the beam. When you assume one section of the beam, you can obtain the corresponding plus modulus, and then compare the plus modulus from your design and the required plus modulus. If the plus modulus for design is larger than the required plus modulus, that means design is okay. Otherwise, you have to increase the cross-section area or cross-section parameters to make sure, okay, the calculated plus modulus from your design is larger than or equal to the required plus modulus. That's all. So this is design, okay? But this subject is about analysis, not about design, so I didn't involve the design issue, okay? And then we have a second case. Okay, in the second case, one end, okay, one end has a zero moment, but for the another end, the moment is equal to 0. Okay, again, for the internal plus hinge section, the shear force is equal to 0. So we can obtain the moment equation for the left free body and the equation for the right free body. The only difference is now for the second free body, just 1 MP. Okay, because this MP is equal to 0, so we can obtain equation and we can eliminate MP and obtain the solution, obtain the equation about x, and then we can obtain the solution about x, and x must not be equal to L/2. Okay, so we can obtain x value. Okay, so here we can obtain another value about lambda. Okay, about lambda. Okay, so now I have